Hello there students. So I have a question from GATE 2008. It's actually a 6 marks question. There are 3 parts to this question, 2 marks for each part. And also you need some basic knowledge from the subject OS, that's operating systems, to solve this question. So let me read out the first part, then we'll try it. Consider a two-way set associative data cache of size 64Kbytes and block size 16 bytes. The cache is managed using 32-bit virtual addresses and the page size is 4Kbytes. A program to be run on this machine begins as follows. So you can just see this program. We have an array of doubles. There are 1024 rows as well as 1024 columns. Also, using 2 loops, we are initializing this array and placing 0.0 in every cell of this array. The size of double is 8 bytes. Array APR is in memory starting at beginning of virtual page FF000 in hexadecimal and stored in a row major order. The cache is initially empty and no prefetching is done. The only data memory references made by the program are those to array APR. The total size of the tags in the cache directory is. Okay, so let's solve the first part. Just see. They've given that cache is managed using 32-bit virtual address. This seems interesting. Generally, in CAO questions related to cache mapping techniques, what they give is the physical address. Okay. That means this one has to be a virtually indexed tag, virtually indexed cache. Okay. See, caches can be of 4 types. They can be virtually indexed, virtually tagged, virtually indexed, physically tagged, physically indexed, virtually tagged, and one combination is physically indexed, physically tagged. Actually, one of them is not used. The most common one is virtually indexed, physically tagged. Okay, this is what is used practically. Most of the L1 caches these days are VIPT. Also, this one is it's just a theoretical concept. Maybe just one processor exists that uses this configuration. Now, PIPT is what you are accustomed to using. Okay, that means most of the questions that you solve are related to PIPT, even though you might not be aware of this, but still it's worth knowing that something like exists, something like this exists. Also, this question is regarding VIVT. How do I know this? Because they're saying cache is managed using virtual address. So it is virtually indexed. Also, they're asking something related to the tag directory. Hence, we need to know the size of tag. That means it also has to be virtually tagged because only data given is related to the virtual address. Okay, let me just talk like for 1 or 2 minutes for this regarding this topic. Generally, the CPU generates a virtual address. MMU using the page table or the TLB technology converts it to the physical address. Okay, so we have a virtual address generated by CPU, then it's converted to physical address, then it's given to the cache. Okay, now scientists wanted to speed up this process, so what they did is they directly just input that virtual address to the cache. That means cache can be indexed virtually. Okay, and in this scheme, virtual index physically tagged tags are still taken from the physical address. Okay, it's actually a very lengthy topic. Let's not discuss it today. Let's keep it for some other day. But with respect to this question, the only thing that you need to know is virtual address is used for indexing into cache. That's it. Okay. Just assume that it's a 32-bit address, very similar to physical address. Actually, this basic information it's required for solving this question is from the operating systems. So, you know, the address is divided into three parts with respect to set associative mapping, that are tag bits and the set bits, set number and block offset. First of all, let's find the split of this address. You know, block is 16 bytes. That means block offset has to be of 4 bytes. Sorry, 4 bits. Okay. Because 16 is 2 raised to the power 4. Block offset is used to identify one of the words present in one block. So number of words in a block is 16. Okay. So 4 bits will be required. Now for finding this set number, you need to know how many total sets are there in cache. So total number of sets can be found out by dividing number of blocks in cache by number of blocks in one set. Okay, that certainly means you need to know number of blocks in cache first. Let's find it out. So what I've done is I found out the number of blocks in cache. That will be cache size by block size. 64 divided by 16. 64b divided by 16b. So you are left with 2 raised to the power 12 cache blocks. Okay, that means you have 4k blocks in cache. Okay, 4k. 2 raised to the power 12 will be 4k. Now let's find number of sets. Number of blocks are these many. If I divide it by number of blocks in one set, certainly I'll get the number of sets in cache. So that will be number of sets in cache will be number of blocks in cache divided by number of blocks in one set. Okay, that means cache size divided by set size. That comes out to be 2 raised to the power 11. Now 2 raised to the power 11 sets are there in cache. This field is used to identify one of them. How many bits will be required in this address? It will be 11 bits, okay, because total is 2 raised to the power 11. So log 2 raised to the power 11 will be 11. Now finding out tag bits is simple, okay. They have given, we are using a 32-bit virtual address. So 32 minus 15 will be 15 plus 2, that is 17. Okay, so we have a 17-bit tag. This total value, it's a 32-bit address. Okay. Now, because tag is 17 bits, the tag directory size, that means the total size of tags will be 17 into the number of tags. Okay, size of one tag into total number of tags. Also, you know that with each and every cache block, we have one tag. Cache blocks are 4k in number. One size of one tag is 17 bits. What will be the size of total or all the tags? That will be 17 times 4k. So tag directory size. So your answer is 68k bits. Because there are 17 bits in one tag, we have 4k such tags because there are 4k cache lines or cache blocks. 17 fours are 68. This k is written as it is. Unit of 17 was bits. These are 17 bits. So its unit will also be bits. and this 4K didn't had any units. It's just the number of blocks in cache. So answer to the first part is 68K bits. Okay, let me now clear some space. So now let's try solving the second part of this question. Let me read out the statement. Second part is, which of the following array elements has the same cache index as APR00? Okay, now they're talking about this array, this one. In question, this is the code that they're trying to execute. Look, there is an array of 124 rows, 124 columns. Then we have these two nested loops which are used to initialize each and every element of this array to 0 or 0.0 because it's an array of doubles. Now they are saying first element of this array, base address of array is beginning of virtual page this. Okay. Then which one of the following, they have given 4 options, which one of the following will have same index as A0, 0? First thing is, let's find its address. This one is not the address. Please don't confuse FF00 with the address of array or base address of array. Look, this is a 20-bit value because we have 5 hexadecimal digits, but address must be 32 bits. So this is certainly not address. What is this? They have given beginning of virtual page hexadecimal FF000. That means this is a page number. Just see, virtual addresses can be divided into 2 parts, that is page number and page offset. Okay, this is also division of a virtual address. This is also division of a virtual address. This division you will study in the subject operating systems. It's used for translation purposes. You'll translate a virtual address into a physical address using page tables. Okay, there you will divide virtual address like this. This is used for indexing into cache. Okay, just for checking whether some cache line contains a particular address or not. We divide virtual address like this in case of a virtually indexed tag. So both are the divisions of virtual addresses only. Also, they are saying base address of array is first address in this page, beginning of this virtual page. So page number is given to us. Base address of array is not given. Rather, the page number of that address is given. So page number is FF000. Also, they have given page size as 4 KB. 4 KB means 2 raised to the power 12. That means page offset has to be a 12-bit value. Okay, so this will be 20-bit. This will be 12-bit. Now, this page number, its first address has to be any address corresponding to offset 0. 0 in 12 bits means 0, 0, 0. Okay, these are hexadecimal digits. So the entire address of this array becomes FF00000. This is the address. This now will be a 32-bit address. Okay. Now they've given you 4 options. That means you just find the address of each and every 4 options and then we'll just compare it. Okay. So let me just see the first option. It was APR0, 0,4. The second one was APR4, 0. So what we are going to do is we'll find these addresses, means the addresses of these elements, and then we'll compare. So first one is already done. APR0, 0. Address of this element will be FF000. Let me convert it in binary. So this is the address of first element. Now, for first element. Now for obtaining this address, we used this division of virtual address. Also, this is a division of virtual address as well. So using this division, find out the set number or index part of this address. That means let's find out what is the index of base address of array, or you can say the first element. So you need the middle 11 bits. That means just leave last 4 bits. So you leave this part and count 11 bits from here. These are 4, then 8, 9, 10, 11. So till here, okay. That means the given element lies given element corresponds to index 0, 0, 0, 11 times. Okay. Now let's find out the index of option A. Option A was APR 0, 4. Okay. Zero comma 4 means the fourth element in zeroth row. Let's find out how many bytes will this element be away from this one. That means let's just find out. If we start from here, how many bytes do we need to skip? That way we'll get to know how many addresses we have skipped. So just add those many addresses into this to get address of this. So from 0, 0 if you start 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. To reach this element 0, 4, you have skipped 4 elements. Okay. Saying that you have skipped 4 elements means how many addresses have you skipped? 1 byte takes 1 address. So 4 elements will take 8 into 4, 32 bytes and hence 32 addresses. Okay, because each byte has an address. That means saying that you have skipped 4 elements is equivalent to saying that you have skipped 32 addresses. Okay. So if you add number 32 into this, you will get address of this one. Okay. 32 will be 1 on the 5th position from right hand side. That means 0, 0, 0, 0, 0, 1. Okay, so this one will be a 1. You add, rest all will be zeros. If you add this number into this, let me just write it properly. So this is 32 in binary. So add both of them to get address of this one. It comes out to be, okay, so address of this one is for FF000 Okay, let's compare if the index part, that means these middle 11 bits are similar for both of these. So last 4 bits are left. Then you need to take the middle 11 bits. They are not same because here we have a 1. Okay, so both are having different index values. Okay, so let's now analyze the B part of this question. It was APR 4, 0. Okay, so here we have a 0 and here we have a 4. So this means row number 0, actually this is 4th row first element or 0th element, and this means row number 0 is completely skipped, row number 1 is completely skipped, row number 2 is completely skipped, row number 3 is completely skipped. So saying 4, 0 means you have skipped 4 rows completely, and now you are on the next element. That means 5th row, 0th element. Okay, saying that you have skipped 4 rows completely means you have skipped 1024 elements 4 times. Okay, each row has 1024 elements. That means to address of this element 00, to its address, you are going to add 4 into 1024. Okay, wrong. 4 into 1024. These many elements are skipped, not these many addresses. Look, one element consumes 8 bytes. Hence, it consumes 8 addresses. So 4 into 1024. How many addresses will they consume? That is into 8. Okay, because each element is of 8 bytes. So it will be these many bytes or these many addresses, because 1 byte consumes 1 address. Now you see 4 into 1024 means 4K. Let's make this calculation simple. Instead of converting it into binary and adding it, I have one more plan. Size is 4KB, page size is 4KB. Also, we can find 4K here. This one will be 4K. Okay. That means we have skipped 4K pages 8 times. Okay. Just try to understand. How many addresses are there in one page? There will be 4K. Okay. So we are skipping 4K pages 8 times. Now, from this address, FF000000, if you want to skip 8 pages, what will be the address? This is beginning address of some page. So if you skip 8 complete pages, whatever you will get will certainly be beginning address of some page. That means last bits will have to be 0, because it will also be the beginning address of some page. Now this is page number. So from here, if you want to skip 8 pages completely, you will reach FF008. Okay. So this is the address of this element. Now convert this address into binary. Look, FF00 is okay. FF00. 8 has to be changed. That means you are going to get a 1 here. Okay. And all remaining bits will be zeros. So 0, 0. That means this one will also be a 0. And this one is anyway 0. So you see, this part is similar. Okay. This one and this one is similar. That means both of these addresses, address 00 and address 40, APR 00 and 40, they have same set number, which means the index used for purpose of placing them into cache is same. That's what they're asking in question. That means answer is option B, 40. Now there's no need of checking option C and option D, but still you can just check them for purpose of your practice. Okay, now I think there's one more part to this question. Let's read that one also. The hit ratio for initialization loop is, so they've given 4 options: 0%, 50%, 25% or 75%. That means you need to find the hit ratio in percent. That means out of n number of times, how many hits are you getting? You see, block is 16 bytes and double is 8 bytes. Okay, that means in one block, you are trying to place 2 doubles, or this can be rephrased as, in one block, you are trying to place 2 elements of the array. Okay, so let me just write it down here. One block will contain 2 doubles. Okay. Now you see, we are accessing this array in serial order. That means element number 00, 01, 02, 03, 04, 05, 06, so on. That means first row, second row, third row, fourth row. Why have I used this word in serial order? Because in question they have given row major order is used. That means these elements are saved row by row. Also we are accessing row by row. So from this loop you can see I changes very slow, but J changes very fast. Also I is the first index, J is the second index. That means row number changes very slow. So row number remains same for 1024 elements in the order we are accessing. So we are accessing like 0, 0, 0, 1, 0, 2. This remains 0 for 1024 elements. That's the reason I can claim that these are being accessed in serial order. Now, whenever you access element number 0, that will be a miss because you are accessing it for the first time. They have given cache is initially empty. For the very first access, that means I is equal to j is equal to 0. This address would not be found in the RAM. Actually, this is the first element. What I mean to say is 0, 0. Okay. This would not be in RAM. That means this is a miss. So this entire block will be brought into the cache. Maybe I used the word RAM. I meant cache. This would not be present in cache. So we'll bring it from RAM. Now you see, each block contains 2 elements. That means even if miss was for 0, 0, you will also bring 0, 1 along with it only. Okay, so this is one block. This was miss, this is a hit. That means after accessing 0, 0, next element to be accessed is 0, 1. And it will be found in cache because you brought it during the previous access. The next access will be 0, 2. Now this block is not in the cache. This one will be a miss. For just servicing this cache miss, you will bring the entire block. That means along with this, you will also have 0, 3. Okay. So this is miss, this is hit. Similarly, you can see in each and every cache block, there will be one miss, one hit. So hit ratio is 50%. Okay. Now some of you might get a doubt that if we keep on bringing a lot of blocks into cache, maybe some of these will be replaced. After say bringing n number of blocks, this one will be replaced. Yeah, it's possible. We don't even care because this block is anyways not going to be accessed for the second time. Either it stays in cache or it's replaced. We simply don't care because we are accessing in serial order. 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, so on till 1, 0, 2, 3, 1, 0, 2, 3. We don't care if it stays in cache or it's replaced. So for total number of accesses, half of them are miss, half of them are hit. So hit ratio as well as miss ratio, both are going to be 50%. So answer to the third question is option C, 50%. Okay, so that's all about this question. Thank you very much for watching this one.